Okay, welcome to the first lecture on graph theory. We start with a very short introduction to how graph theory came about. So, the graph theory originates with the story of Königsberg bridge problem. So, there is a city called Königsberg in olden day Russia, where the river Pregel runs through the city, and this uh, river has some islands, and there are two islands which are nearby, and these uh, islands have some bridges that connect themselves and to the both sides of the river. Now we represent this by A B as the two sides or banks of the river, C and D are the islands, and the edges and the bridges are represented by this figures like this. Now the story says that one is asked if it is possible to visit uh, or go through all the bridges exactly once and come back to the starting place, or at least if you can start from some place and go through every bridge exactly once without using any other modes of transport. Just walk through the bridges. Now, so these are the 7 bridges that is given. And this question, was asked to or suggested to one of the famous mathematicians, Leonhard Euler, and Euler, and Euler, immediately figured out that the only relevant information that we need to solve such a question is the existence and the number of bridges that connects pairs of places. So, which means we can discard, the remaining information and just concentrate on what we have, right? Like this. For example, each bank A and B are represented by 2 points A and B. Then islands are represented by C and D, right? Just another 2 points, and we draw this. We draw this line segments, right? The blue lines, which says that is representing the bridges that connects those two places. When it doesn't matter where the bridges are situated, right? It's just that the bridges actually connect A to B or A to C, right? Or A to D or D to B. That is what is important, and how many of them are there between any two, right? A and C or C and B. Now, once we discard this, unnecessary things and just concentrate on what we have, so we have such a figure, right? Such a diagram, and then what is the earlier question of visiting all the bridges correspond to here? It is just that we need to start from one of these points and then go through or draw, right? Draw the edges or draw this line segments or the figure, right? Without lifting our pencil, right? So we want to draw the entire figure without lifting the pencil and without drawing any of the curves or line segments. And if you can do that, then we can do the walk that we wanted. So such kind of questions can be formulated in this form, right? Now, and this kind of a diagram is what we call graphs. Now we will formally define this in a short while, and then we will also formally define this problem, and then try to, in fact, we will solve this question also. And then that will tell you how to not just solve the Königsberg problem, but many other problems that can be related to this. Now, so this, once Euler came up with this kind of setting, he realized that there are many more things one can do with these objects called graphs. So graphs basically abstract out the necessary things, and the reason why it is very important and very useful is that many of the real world problems can be converted or can be or is of the form uh, I know that there are a set of objects or like persons or places, whatever, and then there are some relations like binary relations that connect these pairs of these. So, for example, you have people, and then there are some relations connecting them, right? Then you have nodes in an electrical or electronic network, and then there are these connections between them, right? Wires connecting them. Or you can talk about molecules, like where you have bonds which connect atoms, right? And then you have in World Wide Web you have different terminals, computer terminals, and you have communication networks connecting them, right? And similarly, we can have like telephone network or many kinds of things can be represented in terms of this a set and some binary relations. Then what graphs does is to enable us to uh, abstract out the things and also try to let us visualize uh, the structure behind this kind of objects in a much more you know much more digestible, or like what you call much more easy to uh, visualize form. Now, let us formally define what is a graph, and then and go ahead. Okay. So, an undirected graph. Okay, so we start with undirected graphs. So, an undirected graph, let's say called G, is basically a pair of sets B and E, where the set V is called the vertex set, and the elements of V are called vertices. So these are just some set which could be finite or infinite, and in most of our dealings we will consider finite sets only. And then there is another set E, right, which is of course disjoint from V, which we call the set of edges. And so we have these two sets like V and E. E is disjoint from V, and then there is a function, it's called the incidence function, let's say psi of G, that maps each edge to unordered pair of not necessarily distinct vertices of G. Okay? So what we are saying is that we have basically a set of objects called vertices, then set of uh, objects, sets called edges, which are basically binary relations, and this binary relation is basically given by the incident function. So you can also see this in another way, that we have a set V, then you have some two elements of sets like of V, and this set is called E, and basically the incident function, if you look at in the inverse of this, that can be like all the labels of the edges, right? So you can see it in different ways. So the edges are basically the labels of these things. So let's look at some example. We have a set, let's say V equal to 1 2 3 4 5, and then we have you know a set E is set A, B, C, D, E. Then the incidence function, psi G basically associates A with the two element set 1 comma 3, B with the set 1 comma 5, C with the 2 4, D with 3 5, and E with 1. Now, so here is the graph, right? So B is 1 2 3 4 5, and then you have these binary relations 1 3 1 5 2 4 3 5 1 4. These are the edge relations of the graph. Now, suppose we have an edge E, and you have the incidence function which takes E to the set U comma V, right? U and V are vertices of the graph. Then the edge E is set to join U and V. So the edge is basically joining or connecting, right? U and V, and U and V are called the endpoints of the edge E. Now, here is some standard notation that we will use. So if you put G within two parallel lines, then it represents the cardinality of the vertex set of G, which is called the order of the graph. The order of G is the number of vertices, right? The cardinality of the vertex set. Then similarly, we denote the cardinality of the edge set, which is called the size of the graph G, by two lines on both sides, right? Two parallel lines. Now, another simplification that we use, is that instead of writing the set u comma v, right, we often write just uv, right? Whenever it is from the context, it is clear. We will just write uv to say we are actually meaning, u comma v, right? And especially when we want to denote the edges, right? We will use this. Now here is another example. Let G be V comma E with the matrix set U V W X Y, and the edge set A B C D E F G H. Okay. So we have the five vertices U V W X Y, and then we have the edges A B C D E F G H. Now the incidence function again, psi G is given by A is mapped to UV, right, or U comma V. B is also mapped to UV. C is mapped to UU, D to UX, E to VX, and F to WY, G to UW, and H to UY. Now, you will notice that we have A and B both mapped to the set UV, right? U comma. Now, this is something that we allow in general, but we will restrict ourselves to types of graphs where we don't really allow this when we continue this course. Now, another point I should mention is that we most of the time, or often, we discard the usage of the incidence function ig, and then just write the edges as as the pairs itself, right? So we'll just say that okay, E is equal to UV, VW, and VX, where what we actually mean is that there is some edge which is mapped to UV, another edge which is mapped to VW, and another edge that is mapped to VX by the incidence function. So this is what we usually do. Like we just write, let's say V is equal to 1 2 3, then E is equal to let's say 1 2 1 3 and 2 3 or something like that. This will tell you everything that we need to know about the graph. Now, here is another way of looking at the graph. In fact, this is how we want to look at the graph, because this is what enables us to visualize things. So, Euler, as we saw earlier, basically started by defining such an object and representing it as a figure or diagram that we saw. Right? So similarly, the graph that we presented before, right? Like they can be also represented as diagrams, and these diagrams help us visualize things in a much more clear fashion than looking at the set theoretic definition of the graph. So what we do is basically, given the graph, we identify the vertices of the graph with a distinct point on a surface, let's say the plane. Right? Most of the time we will use the plane, and the edges of this graph will be represented as simple curves that connect the endpoints of the corresponding edges. Okay. So if, for example, you have the graph G with vertex at 1, 2, 3, 4, right, and edge set 1, 3, 1, 4, 2, 3, and 1, 2, then we can represent it as follows, right? So we will just represent these vertices 1, 2, 3, 4 as the following points. This is 1, then this is 2, you have 3, and then 4. So these points on the plane, right, now represent the vertices 1, 2, 3, and then to represent that there is an edge connecting, or there is an edge that joins 1 and 2, right? 1, 2 is an edge, is the represented by drawing a line segment, right, that connects 1 and 2. So this tells us that 1, 2 is an edge in the graph. Similarly, we will see that 2, 3 is an edge, right? 1, 3 is an edge, and 1, 4 is an edge. And because of this, you will see that this is actually representing the graph that we mentioned above. So we have a nice representation, and this figure tells you something more than what you will see immediately from looking at the set theoretic definition. You can see that some structure. Right? So there, you can now like imagine why different graphs. If you look at that, you will be able to see different types of structures present, and that will tell you many properties also of the relation that we are looking at. This is kind of intuitive once we see how drastically our visualization helps to see this kind of structures. Now, suppose in a graph, right? Uh, if like a couple of edges have both have the same endpoint, right? So as in the example before, right, we had A and B are edges, both have the endpoints UV and UV, right? So such edges where we have the same set of endpoints are called parallel edges. Now, if the endpoints of an edge are both identical, right, then it's called a loop. So let us look at an example here. The graph represented here, for example, you see A and B, like 1, 2, and 1, 1, 2, right? So these two edges A and B are parallel edges. On the other hand, and the edge D is a loop. Because the HD has the is basically 3 comma 3, right, represented by D mapping from 5 psi G maps D to 3 comma. So that is the. Similarly, you will see that you have F, G, H are all parallel to each other. Then K is another loop, L is a loop, other edges are not loops. Okay, so we will see these kind of things are also allowed in our graphs. Now, a graph where we don't allow parallel edges or loops is called a simple graph. Okay, so if we have a graph where there are no parallel edges of loops, then such graphs are called simple graphs. Now, most of the graph theory and in this course also deals with simple graphs. So we will be mostly working with simple graphs, and anytime we don't specifically mention whether a graph is simple or not, we will assume it is to be simple. Right? So unless I state otherwise, you can assume when I say a graph, it's a simple graph. Now, a multigraph is a graph where you allow parallel edges for loops. So we are, of course, so examples of both of these. Like, so this graph is a simple graph, and here is a multigraph. Now, if in a multigraph we don't allow loops, then it's called a loopless multigraph. Now, as I just mentioned before, much of the graph theory deals with simple graphs, and we will also use the term graph to just denote simple graph. And whenever I want to make it clear that the graph is not simple, I will add either multigraph or loopless multigraph. So this will be clearly mentioned. Okay. Let us look at few more definitions before we go to some interesting results. So let us look at this graph given above, right? You have the edge E, which is basically joining U and V, right? Vertices U and V. Now, if E is equal to UV is an edge, then we say the edge E is incident to the vertices U and V. So, E is incident to vertex V or as well as vertex U when E basically joins U and V, right? Or if you look at as a set theoretic version of this, you see that because E is basically a two element set U comma V, and V is is a vertex or U is a vertex, we can say that if E intersection V is non-empty, then E is incident to V, right? And similarly, E intersection U is also non-empty in this case. And we say that the vertex U is adjacent to the vertex V, when E is basically joining U and V, right? So if U and V are joined by an edge, then we say U is adjacent to V. And also called a neighbor of V, right? So U is a neighbor of V if U and V are joined by an edge. Now, if you look at the vertex V here, vertex V here, then the other vertices U, W, and X are all neighbors of V, right? So the neighbor set of V neighbor set of V includes the vertices U, X, and W. On the other hand, the neighbor set of U includes only the vertex V. Okay. Now, another important parameter that we want is what is called the degree of a vertex. Now, given a graph G, right? So let us look at the graph that is given below. Eh, if you look at any vertex, when you look at the figure, it's kind of immediate, right? That each vertex has some specific number of edges that are incident to it, right? So the number of edges that are incident to a vertex is called the degree of the vertex. So in this case, for example, the vertex 2 has degree 1 because there is only one edge that is incident with it. Vertex 4 has degree 3. right? Because the vertices 1, 5, and 3 are all adjacent to it. Right? And vertex 5 has degree 4, right? Vertex 1 has degree 6. Similarly, vertex 7 has degree 2. And so we will see that the degree is basically the number of edges incident with the vertex. Now, this parameter is very important, as we will see when we proceed in the course. The so let us look at just a very simple theorem. This is called the first theorem of graph theory, and it is almost immediate, and the proof is immediate. So suppose G is a graph, right? Then summation over all the vertices, summation V belongs to V, degree of V, right? Summation over all the vertices, the degree is twice the number of edges. So can you think of a proof? Just a one line proof you can think of, right? If you just think about it for a minute, you will be able to see it very clearly, right? So how do you prove this? So the proof comes from the fact that given any graph, right? Uh, what is degree? Degree is the number of edges incident with a vertex, right? So if you look at a vertex, the degree is the number of edges incident with. But if you look at an edge, the edge is incident to precisely two vertices. Every edge has two endpoints, right? So the edge is incident to two vertices, and therefore, what we know is that when we count or the sum over all the degrees, right, the edge contributes to the sum one to each of its vertices. Right? So there are two vertices for an edge, so every edge contributes two to the sum, and therefore the sum must be equal to twice the number of edges. So this is a one line proof. Okay? So the proof is that every edge contributes uh, value 1 to the degree of each of its two vertices. And this completes it, right? Okay. Now, another two important parameters are the maximum degree, which is denoted by capital L delta of the graph G, and the minimum degree, which is denoted by the small delta of G. Okay? So these two are the Greek letters delta, capital and small. So what is the maximum degree? The maximum degree of a graph is defined to be the maximum of all vertices of the graph degree of the vertex. So the largest degree that appears in the graph is called the maximum degree. Okay. Now, similarly, the minimum degree of the graph is small delta of G, which is the minimum over all the vertices degree of V. Now, in the previous example that we saw, right, you can talk about the degrees, right? So what is the minimum degree? The minimum degree in this graph is 0, right? Because the vertex 8 has a degree 0. And the maximum degree in this graph is 6 because that is the, 1 is the vertex with the largest degree. All the other degrees are less than 6, right? So therefore, the largest degree is 6 and the smallest degree is 0. For other examples, so in this case, maximum degree is 2 and the minimum degree is also 2. And here is another example. So the minimum degree is 1 and maximum degree is 4, right? So this way, this is a delta. So the maximum degree is 4. So this way, you can define these parameters, and they are very important. We will see its use very soon. Now, a graph is called finite if both the vertex set and the edge set are finite sets. Otherwise, if one of them is not finite, then we say the graph is infinite. Now, again, unless we state otherwise, whenever I say the term graph, right, in this remaining part of the course, it states that the graph that we are considering, right, is a simple graph. It's an undirected graph, and it's a finite graph. Very simple, undirected, finite. Then if either of this is not the case, we will mention it. The graph is not undirected, I will say directed graph. Right? If it is not simple, I will mention that, right? Whether it is loopless or ILO loops, multi edges are not allowed or allowed, will be mentioned, and whether it is finite or not. If it is not finite, I will mention that. So here is an example of an infinite graph. We saw several finite graphs. So here is an example of an infinite graph where we call the graph the graph of the plane. So what is the graph of the plane? Every point on the plane R2 is a vertex, right? So that makes it it's already uncountably infinite, right? So the vertex set is R2, right? Now, what are the edges, right? So two vertices are adjacent. If and only if the distance between u and v is 1, right? Right? I mean unit, some value, right? Whatever, some fixed length. So which means that if you look at the plane and then just take any point, right? This vertex, right? The corresponding vertex is basically adjacent to all the infinitely many points on the on the unit circle that is around this point, right? So and this is true for every single point. So you can assume the graph is really huge. But we can still study this and look at the several properties. We will even try to see how to bound the what is called the chromatic number of such a graph. And things like that. We will see these things later. Now let us look at a few special graph families because they come very often in our discussions, and they are very important because they have very nice structural properties which can be useful for solving several questions. So here are some such graphs, right? So graph families. So one of them is what is called a complete graph. So a graph is complete if any two vertices in the graph are connected by an edge. So any two are adjacent, then the graph is a complete graph. So let us look at an example of a complete graph. The vertex by itself is a complete graph, right? There is only one vertex and nothing else. And therefore, any two of them are adjacent. There is only one, right? Then, suppose you have two vertices and there is only one edge possible connecting them, right? Therefore, that is also a complete graph. Any two are adjacent. Then you can look at 3 or 4, let's say 4. Right? So in this case, you have all the 4 adjacent. Right? This is another complete graph. Then you have this graph where you have any all the 5 vertices and any 2 vertices. Right? So these vertices are usually denoted by because we know that once you know the number of vertices, you know all the edges are going to be present. So therefore, you know the entire structure about structure of the graph, right? So we usually denote this graph by k subscript n, where n tells you the number of vertices in the graph. So this is the graph k1, big letter K, the capital K, subscript 2, and K4, K5. Similarly, you can define K3 if you want, right? And for any positive integer, we can define complete graphs. Then, on the other hand, suppose no two vertices are adjacent, then the graph is empty, right? So you have these vertices but no edges. Suppose you have a set of vertices but no edges, then the graph is called empty graph. Now, an independent set. So, this is another notion which is important. An independent set in a graph is a subset of vertices where no two are adjacent in the graph. So, here the difference of this to the empty graph is that the empty graph says that the entire graph is edgeless. On the other hand, here we are looking at a subset where between those vertices in the subset there are no edges. Right? So, let us look at this graph. Okay, let us look at a graph like this, right? So in this graph, I want to find an independent set, let's say, right? Some subset which is independent. So let me start with one vertex. I add it to the set I. Right? This is a part of the set. Then I will not be able to pick this vertex or this vertex because these two vertices are already adjacent to this. Which means that if I add, let's say, let's put some names. Right? This is 1, 2, 3, 4, 5, 7, 8, right? So if I pick one, right, to be in the independent set, right? So let's say I is equal to. So if I put one to the set, then I cannot put 2 or 8 or 6 to the set, right? Because if I put either of them, right? If I put 6, for example, 1 6 is an edge, which is not allowed in an independent set, right? So therefore 1. But now I can put any other vertex. For example, I can pick 7. So I can put 7 to the set. Then if I have 1 and 7, of course 6 is adjacent to 7, I cannot put. 8 is also adjacent, I cannot put. But on the other hand, I can put either 3, 4 or 5 because none of these are adjacent to. So suppose that I put let's say 3, right? Now if I put 3 to the set, so I have what are the things I have? I have 1, then I have 7, and then I have 3, right? Now, if I put 1, 7, and 3, then once I add 3, I cannot add either 4 or 5 because 4 and 5 are both adjacent to 3. Right? So, this is one independent set I have 1, 7, 3. Of course, 1, comma 7 is also an independent set. 1 by itself is an independent set. But 1, 7, 3 is also an independent set. Now, suppose I did not add 3 to this, right? Then I could have, instead of this, I could have added 4, let's say, right? Now, instead of adding 3, if I added 4, I could also select 5 to be part of it because 4 is not adjacent to 5. None of this is adjacent to 5. So, I can say that, okay, so 1, 7, 4, 5 is also an independent set. Right? So this way we have several possible subsets we can find which are independent. Okay. So yeah, so we have this set. Then of course you can find other independent sets. I can start with just 2, then I can add 8, 4, 5. Right? You can find such independent sets. Now, uh, a very important class of graph is called bipartite graphs. The graph is bipartite, right? By the name itself suggests it, right? If you can basically partition, right, the vertex set into two sets, right, two subsets. So bipartite means that two partitions, right, two parts, two subsets, let's say x and y, such that every edge in the graph has one endpoint in x and another in y. So I have a graph where you have some vertices, right? I can partition the vertex set into two sets, let's say 1, 7, 3, 8, then 2, 4, 5, 6, right? Right, let's say. And then every edge in the graph is basically having one endpoint in x and one endpoint in y. Something like this. So in this case, what you know is that you cannot have, for example, edges like this, right? 1, 7 edge is not allowed, right? Because then this property is not true, right? That every edge is of the form with one endpoint in x and one in y, because both are in one side here. So let us call this as x and y, right? So suppose we have something like this, then what we can immediately see is that the set x and y are both independent sets, right? So the graph is bipartite. You have a bipartition of the graph into x comma y. Then both x and y are independent. They must be independent sets, because if it is not independent, then the condition clearly is not true, or the what is given is not a uh, partition into the according to the definition of the bipartite. Now, a related concept is that of the complete bipartite graph, where you not only have these pairs of these two sets of vertices, but between any two, right, in any vertex in x and any vertex in y, there is an edge. So then we say the graph is a complete bipartite graph. So let's say that I want to look at a complete graph KMN. KMN is that you have m vertices here and n vertices here. Okay. And then every possible edge is there. One connecting to each of these. This connects to every other vertex. This also connects to every other vertex. Right? So such a graph is called a complete bipartite graph. So here is an example graph A, B, C, D, E, F. I want you to look at this graph and find out a partition this vertex into two sets such that it is a bipartite graph, and verify whether it is a complete bipartite graph or not. So you can think about this question. You verify if it is complete, right? Complete bipartite. Okay. Another important class of graphs are the path graphs. The graph is called a path, right? if you can basically find an order of the vertices, right, in a linear order of the vertices, such that the vertices are adjacent if they are consecutive in the sequence. Okay? So you want to find a sequence such that the vertices are adjacent if and only if they are consecutive in the sequence. For example, if I have v1, v2, v3, v4, v5, then as a sequence, then v1 to v2 must be an edge, v2 to v3, v3, v4, v4, v5. So the edges must be present and no other pairs form an edge. So such a graph is called a path graph. So for example, here you have a path graph with 4 vertices, 1, 2, 3, 4. And here is another graph with 6 vertices, 1, 6, 3, 2, 4, 5. Right? So these are path graph. Okay? Now, given a path graph, the number of edges in the graph is called the length of the path. So what is the length of the path? Pn. So Pn is the path graph on n vertices. Okay, and the length of the path graph Pn is equal to n minus 1 because with n minus 1 edges, uh, we can connect these vertices. Similarly, a cycle is basically a graph where you can find an order, a circular order, right, cyclic sequence of the vertices, such that the adjacency is basically when they are consecutive in the order, right, in the sequence. Otherwise, they are there is no edge. So examples of cycle graph are given here. C8 is a graph on 8 vertices, which you can put into this order. Right? Similarly, C3 is a graph with 3 edges. C4 has 4 vertices and 4 edges. And the length of a cycle is again the number of edges, and it happens to be n for the cycle Cn. Okay, so C suffix n denotes the cycle graph, usually, right? Denotes the cycle graph with n vertices, and it happens to have also n edges. Now we say a graph is connected if for every partition of its vertex set into two non-empty sets, let's say x and y, you can find an edge with one end each in the sets x and y. Okay? Otherwise, it is called disconnected. So when is the graph connected? Right? If you can partition the vertex set into two non-empty sets such that there is an edge in one uh, end in each part, right? So I can do, if I cannot do that, right? If I cannot partition such that one endpoint, if I can partition such that for some x and y, right? There is no edge connecting x to y, then the graph is disconnected. So there are two graphs given here, right? The first graph, which is on the left side, right? Let's say G. The graph I claim is to be connected, which means that no matter how you partition, you will not be able to you would find two sets where there is no edge between those two. You cannot partition the vertex set in such a way. So this is something you can try, right? Try different subsets and see whether you can do it. On the other hand, the right hand side, the graph I say is disconnected because the given partition, right? For example, the 1473, right? It's one set of vertices. 256 is another set of vertices. So that partition will tell you that there is no edge that connects this set x and this set y, right? So therefore the graph is disconnected by that. Now we will come up with other related definitions for a graph to be connected and then show that they are actually equivalent. The complement of a graph, let's say a graph G is given, then what you do is that you look at the same vertex at V of the graph, where if two vertices U and V are adjacent in the graph G, then I will make sure that they are not adjacent in the graph, let's say G bar, right? And then if two vertices like let's say X and Y are not adjacent in G, then I will make sure that they are adjacent in G bar. So such graphs are called, such a graph is called the complement of the graph G. So here is an example graph, which is a cycle graph on 5 vertices, right? 1, 2, 3, 4, 5, and it's a complement, right? Which is also a graph that is represented by the star, but it actually happens to be also a cycle. You can verify that it's a cycle. There is an order which will tell you that it's actually consecutive with respect to that order, cyclic order. And one can easily verify that the complement of the complement of a graph is the graph we started with. And if you want to look at more examples, we can look at some examples. Right? So what is the complement of this graph, right? So there are 4 vertices. So I can just represent these 4 vertices. And this edge is missing, right? Then this edge is missing and this edge is missing. So this graph is the complement graph of. And yeah, one can look at several examples if you want. I mean, if you just take the complete graph on 4 vertices, its complement will be the empty graph on 4 vertices. So this way, one can look at. Okay, I think we will stop at this time and then continue with further topics in the next class.